first time visitor of the meeting. So Andreas is going to talk about truth and probability.
Yes, thank you very much. It's a good custom to thank the organizer for the invitation, which I really would like to do this time, particularly, and also thanks for the session because of this grant that makes it possible for me to be here. All right, I want to talk about something which actually relates quite a lot to the previous talks, more than I had expected. So the title of my talk is Probability and Truth, not quite as bonkers as the title may suggest, and it's based on this paper from February. It's in the archive. It's a paper by Chris and me, and I'll just give you the archive number. And what we already heard in the previous talks is that interpretation of probability is a difficult thing. That's one of the debates that's actually older than debate on the meaning of quantum theory. I just want to mention a few things. I will tell you what my favorite interpretation is and where this the maths I will show fits in. But most of what I say can potentially be useful from different perspectives. So it's not just useful for a certain interpretation of probability. But anyway, what are interpretations? Interpretations can be a frequentist. Most physicists, I would say, fall in this category. So, say probability is, well, not quite the relative frequency, but it's what the relative frequency tends to. It's approximated by relative frequencies.
Are we allowed to boo and cheer at very?
Oh yes, please, please. Yeah, you should interrupt me at any point you like, even if I shouldn't get to it. So my goal for today actually is to show you a logical version of the Born rule. But it's actually I only have 45 minutes left in the group class. So, okay. Anyway, there are recently very popular Bayesians. So it's about what odds you would accept if you had to make a bet. That's what probability is about. So it's more a state of knowledge or a state of information you have about something. And finally, maybe less well known, propensity interpretations. Propensity is something like inner tendency to be this or the other way. And then, of course, there are other criteria you can distinguish. You can talk about, let's say...
That seems to be not a particularly coherent idea, is it? Propensity?
This is the one I prefer. So,
so how does one distinguish it from frequentist, for example? You're saying inner tendency. How does one observe such a
physical,
I
right?
admit that it's a fancy word which sounds, well, latency, and it has some suggestive appeal to it, but it has to be made more precise, I think, what it means. You may distinguish epistemic versus, well, epistemic just means lack. You interpret probabilities as well, you have a lack of knowledge, versus irreducible probabilities. I don't actually know if that's the usual word, but it gives a good idea of, for example, in quantum theory, a pure state does not completely specify the outcomes of experiments, so even if your knowledge is maximal, there may be an element of probability which cannot be reduced by gaining further knowledge. And then, of course, is classical probability the same as quantum probability? Yes, in which sense maybe a bit different. And there's an enormous amount of literature on all kinds of combinations between these things, and it's a long debate, and basically going on for 50 to 100 years. So I've not solved this, but in a sense it's important when we do physics and if we want to explain things and foundations that we commit ourselves to saying what our interpretation of probability is. Here I want to show you attempts to, we can either say replace probabilities by truth values in a certain topos, or you can also say you try to understand probabilities as truth values in a certain topos. It's a very simple idea, as you'll see. We take two steps. The first step is we find a topological space X such that the open subsets of X correspond projectively to numbers between 0 and 1 to usual probabilities. So of course you would think, let's take the unit interval for X, and basically what you do, I'll show you what to do precisely, and take, and this may be somewhat surprising, as we said, the open interval 0, 1, and define opens of the form 0, R for R here 0, 1. One thing I have to make clear that should be clear, but just to be precise, 0, 0 is the empty set, right? And if you do it this way, you get the projection better from the unit interval into the opens of this. Now it's a space, and if I group the space with these all lower sets, obviously, in this topology I write it 0, 1 the low index L, and obviously you just have to set R to 0. So maybe wonder, is this the best choice? Do this. Why don't we send, for example, R to 0, R? Well, these half open intervals are not closed on arbitrary unions on one topology, so it's better to use these guys. Why don't we include 0? Well, we need the empty set as element in our topology. The most natural thing is to take this corresponding to 0, and this goes to the empty set. But this is why...
If you subreply, you put the 0 back in anyway, so it's kind of...
Yeah, I'm sure this relates to many things that have been done before. This is a pretty straightforward thing, and that the axis here may have seen more of these things than I. Please tell me. I constantly slip into writing my ones this way, which sometimes confuses English. I cannot avoid it. This is a 1, it's not a 7 or anything. Alright, and the next step is then take the topos of sheaves over this space, and okay, I don't want to say much about sheaves at the top. Actually, I want to keep these things to a minimum. Think of contrariant functors from this subset into sets, and then you have free sheaves, and so sheaves need a certain completeness condition on which we will not talk here. Why do we do this? Well, then by standard result from topos theory, you have the following. There is projection. Let's call this one sigma from the opens, the underlying space, so that's the base category of our topos, into the global elements of a certain object called the sub-object classifier. And these global sections are nothing but the truth values you have available in the topos. So what we've done here, we've just defined mathematical universe, a topos, where our truth values in certain open sets. Then of course we look at this, these open sets exactly correspond with probabilities. So we can compose these two things into given limit, and then say we can talk about probabilities as truth values in this topos. Okay, before we do so, I want to get rid of this. Is very cumbersome to write. I'll just write omega 0, 1. This is meant to be this omega sheaves 0, 1. Okay, so just say this again. These are the truth values in this topos. Okay. Next thing to do, indicate this we compose. Let's do theta and do sigma, and we get L is minus sigma of the theta. This really goes from our probabilities into global sections. So the classifier, and how is this done concretely? Let's say, well, this is another bit of language from the topos here. The stage is nothing but one of these open sets here, so for all stages 0R the following way. Why? You take a probability, so for all P in 0, 1, you find L of P at stage 0R as the following, so I can see that there's not enough space here to go to the next line. So you get a certain set of open sets, namely all the open sets of the form 0R prime in the open sets of our space, such that R prime is smaller or equal to R, and that is nothing but a component of this sheaf at stage 0R, and this is P is greater or equal to R. So that looks a bit mysterious, but not saying really much. If you have that your probability in this number between 0 and 1 is greater than or equal to this R, which determines the stage you're looking at, then you get every open set of the form 0, R prime up to 0, R itself. This is nothing but the maximal collection of open subsets of 0, R. It's nothing but the maximal sieve on this stage in the topos language. So what happens if we have R is smaller than P? I get a similar set of open subsets, but now you have, of course, this only up to R prime is smaller equal to P. So you should think of this that at stage R, you have all the sets available which are contained in here at alpha from 0, r prime. Here we collect all of them because our p is bigger than r. Here only collect them up to level p. And this happens if it's greater than r. Well, let me make one extra assumption. 0 is smaller than p is smaller than r. And it's useful to make this explicit. You get the empty set if so this looks slightly difficult. It's not really difficult.
I think how would one read these stages? It's hard to get a feeling for that.
Okay, let me rewrite this.
Probability.
Yeah. Let me rewrite this slightly. I'll say more on this. Let me rewrite this slightly. I just want to use, instead of having these open sets here, I use this projection pattern, so I go back to the actual numbers. That already clarifies things a little bit. And so this is isomorphic to the following. We get the interval of 0, which is nothing but let's do it. Which is if it's going to be equal to 1, so to p 0 smaller, p smaller r. I should think of this, well, it's a truth value in this topos, and it cuts out at each stage exactly, well, possible this, all probabilities between 0 and p, if they're available. If you only have the probabilities up to r available, take all of them.
So am I supposed to
And
think
you
of,
can think of, sorry, yeah.
am I supposed to think of these stages as like I develop a greater and greater understanding of what the probability space is as our progresses?
Good. Well, I'm not sure.
My problem is, are they really to be thought of as probabilities and have a bit of a feel of fuzzy sets or something like that?
Well,
Degree of,
easiest way to get back to probabilities is you take, as usual, the inverse image of, I'll correct this function of everywhere where you have the maximum. This gives you back some open subset. This open subset is always from 0, r. Then you go back using better to probability. It's just rewriting these as truth values in this topos, and
alright, but where are the probability distributions?
we'll come to this. Yes, that's of course the next point, and I'm almost there actually. Yes, actually that's the next thing I want to do. So one little observation I want to make here, let me know if you see before I write this stuff. Well, both beta and sigma are isos, and it's well known that these truth values form a Heiting network, complete Heiting network. It's easy to put the complete Heiting network structure here, and this is not just a set iso, it's actually an iso of complete Heiting networks. So the observation is L is iso. This is something, especially when you think about means and negations, that seems to be a bit coincidental to see in a minute. There's one aspect to that we will be using, namely L preserves joins.
So is the order there distribution?
It's the usual order. So in particular, this means our L preserves joins, and this we will use to characterize things like sigma additivity of measures. So we will now look at probability distributions for measures. We'll write this stuff first. to now I'm talking about classical probability, and I'll go on to do this for a few more minutes. And the second half we'll talk about what we can do for the quantum situation. It's good to read this. So, how do we talk about probability distributions? I want to talk about probability measures actually. So, we have, say, mu from sub x to 1 is a is everybody familiar with this, or should I say what the defining properties are? Maybe it's useful to say. So I don't want to assume much. So first of all, just write sub x. These are the new measurable subsets. So basically you assign sizes or weights to a distinguished family of subsets, and those that you can measure, those which are measurable may well depend on mu. So first thing I want to say is sub x is a new measurable substance. X. Typically, this is some signal algebra. I don't want to assume very much at this point. Then you have that the whole space is always measurable, and this goes to 1. And the second thing, which is a bit weaker than you would probably normally see, if you have x1 potential x2 is empty, then mu of x1 union x2 is x1 plus x2. There's a certain additivity condition is when you have two measurable subsets which are disjoint, and the measure of them is the measure of the union is the sum of the measures. That together, this implies, for example, that the empty set goes to 0, and that's all I want to demand at this point. If you're more familiar with measure theory, then you know that this is just the first step. This is a condition on finite intersections, but usually you want, if you have a countable family of pairwise disjoint measurable subsets, then you get a countable additivity condition. We characterize this as a certain joint preservation picture. So I want to leave this open for now. So this is just saying, okay, I have some set of outcomes and to certain subsets is fine.
And Andreas, if you're in a situation where you've got the complements of sets as well, because you've got all the measurable. So from those, can you deduce the usual modular law that without the restriction that they're disjoint, for an arbitrary one, you can get the other one as well?
Yes. Yeah. The usual modular, what he refers to is the following mu of x1 join x2 minus mu of x1 essential x2 is mu of x1 plus mu of x2. This is, if they overlap, obviously I have to subtract this. No, actually, sorry. This is because this is exactly the part that's counted down. Yeah, so this is.
Well, if you write it the other way, then you track it.
Yes. I was.
Just how something like that generalizes to the
I was confused. But yes, this follows. Okay, so this is something that you just have in probability theory normally. So what we can do now, let's just go from here with our map L that we constructed to certain truth values in the top. So let's look at this. So I'll just diagram. You have sub X here, you go by measure mu to probabilities, and then you go by this map L to go to sections. So specifying this topos, and of course the question becomes, is there something I can put here which will allow me to get a commutative diagram, and then I want it in a way such that here I'm only talking in logical terms, while here it's more of a standard probability.
So all this is happening in set, is that correct?
All this is happening in set, yes.
So
This is
they
classical.
externalized the
Yes.
points of your subobject classifier,
Oh yes,
and
yes.
then everything else is living in set.
Yes. Then, well, as usual, I'm looking at this first, and then.
No, just to clarify.
But it's true, yes. Now, let me tell you what you can put here, and it's actually quite simple. Let's say you take S in these measurement subsets. We find a sheaf. Well, obviously it should be a sheaf over the same space category, so it should be a sheaf over this topological space. Let's call this sheaf as underlined, and okay, fancy way of saying this, I look at the Ital bundle over 0, 1 with constants called S. But it basically means for every number between 0 and 1, you get one copy of your original set S. And okay, so let's try this.
Because usually there are no, so it's just I mean, there's no co-equal, it's all kind of disjoint.
Yes, it's really disjoint. I want to be able to talk about every probability.
So the co-element sort of is just a co-product.
Yes, exactly. Okay, so if you're familiar with this, it's what we just said. If you're not familiar with it, just think of taking your S and getting to 0,1 many copies of it. For every value of 0, 1, you get one copy of this. That's the whole idea we're doing here. So you can do this for every element in X, and what we get is something like this. It's a little bit of information on this. You can of course apply this construction to X itself. This gives you X underlined. And now if you start from a level subset of X, you get this X underlined, which is, for example, S, which of course then is a subobject of this X underlined. There's nothing much happening. This is actually the boring part. The interesting part comes now. This will define this arrow here, obviously. The interesting thing is how do I get from here to truth values? Let's write this down now. So,
Andreas, does big delta preserve some things?
well, it's
On the right,
just, it's a big coproduct.
On the left, you write it as sub, but it's a different kind of sub, right?
These are subsets, these are subobjects.
The
Yes.
rest are measurable subsets, the rest are open subsets.
These are measurable subsets, and these are also measurable subsets. So I could be more precise and write a little M at each point. Maybe that would be, well, it would be more precise. I haven't, strictly speaking, I haven't defined what measurable subsets over here should be, but it's really just taking copies of things and continuously making copies of this.
So it's kind of S cross usable, isn't it?
Oh, it's exactly that, yes. So we've now actually found that this will use here, and fill in what will happen here. This will use sub sheet 1L of X. The interesting thing is what happens here, and this of course should be determined by our mu. Now, mu determines the following thing. Determines sub object of Ex. This is, again, the proper sentence, this is the power object of this object X underlined, and X on, you can think of this as all the subsets of this. And how does it work? Well, all are in 0, 1. Define T mu, where should I underline this? 0 R to be, well, something very simple. At this stage, 0 R, you have one copy of this guy here. And we want to single out a certain subset of this, and in terms of our measure, the obvious thing to do is just take the S contained in sub X such that mu of S is greater or equal to R. So you collect, and at every stage 0R, all those subsets whose measure is at least R. Okay. And now we actually can do something very simple and very nice. And in the topos of sheaves over 0, 1, L, we can interpret a certain set theoretic formula, namely S is in T mu. Mind this. So what we're using here is an aspect of topos theory that basically every topos is like a universe of sets. So you can look at such formulas. Of course, that's written in set theoretic language. You can interpret such expressions in an arbitrary topos. And just like this gives you, if you read it in set, it gives you truth value in set, such expression interpreted in the topos will give you truth value in the topos. So we will actually be mapping from here to here, and it turns out that this will give us a commutative diagram. So let's write this down. So for all R 1, we have like these semantic brackets. So this is what you interpret this set theoretic expression in your topos. You have these semantic brackets which indicate that you have such application. And at stage 0 R, this is, I rewrite this in a few different ways, and let's see, I think, how it works. So, first way of writing this is all R prime smaller or equal to R, such that S at stage 0 R is in T. So it is not prime. Okay, what does this say? Well, I collect all those numbers, or 0 and 1 obviously, for which the component of S at stage 0 R prime is in this collection of sets which have measure at least R. You can rewrite this as things here. This component, I should say, this is nothing but S itself, because we constructed this way. So we take one copy of S for every number R. So this is nothing but S. And
So, I mean, is the idea that instead of having a sort of thing living inside the topos with all these stages, you flattened it out into a single set theoretic object, so you can make this diagram and compute it as a set. Is that a fair way?
it is a fair way of saying it. So I would actually argue that this is pretty trivial in exact and classical probability. I would say why. One thing one may say, if you want to think about probabilities in an objective, there's another subjective versus objective probabilities. Propensities are potentially on the side of objective probabilities. If you want to think about probabilities in an objective way, this may be one way of describing them in a purely logical way.
I think it's a mathematical construction.
It's a mathematical construction, but it lends itself to a certain interpretation, arguably. But this, of course, as I said, you don't have to follow this interpretation. The interesting thing, actually, and probably I won't have time to do all of this, is there is an exactly analogous diagram for the arbitrary quantum states. It looks just the same yet. Things which are actually really analogous to all four of these. That's quite nice, which is not so obvious. This means that we can talk purely in logical terms on the suitable topos about mixed states, and instead of talking about probabilities, we can talk about truth values. Okay, maybe just final way of rewriting this. If you play around with this, let's rewrite it at least once in terms of open sets, because that's actually what we're looking at. This is following. Okay, now, again, this is known from topos theory that this expression here, which we wrote down here, this is the truth value in this topos. We actually map here. So let's write, to find the final mapping, we have the psi mu. This goes from sub L x to long sections like that. So 1, and it sends an S to S. And this is exactly the map we put here. It's very easy to check that this gives exactly a converging diagram. Of course, it has to be checked, but what I want to emphasize is if you look at this part of the diagram, you're only doing logic, using one logic suitable topos. This part you do standard probability theory. So that is just saying you can replace classical probabilities by truth values in this topos. And so now I'm going to do it for time. 20 minutes, okay. How do we do this? So my claim is you can do the same quantum theory. Well, not exactly the same, but very, very similar. And for this we need one result about quantum state, which comes from the topos approach. So I'm not saying much about the topos approach, but the basic idea is you look at the quantum system. First of all, it's described by some algebra of operators of Hilbert space, and this is a non-commutative algebra, of course. So you can take, actually take various technical reasons from Neumann. So let's say we have a phenomenon algebra n, and you can always think of this as being bounded operators in some Hilbert space. All the arguments work in general, but it's totally fine to think of some fixed Hilbert space in this thing. It's okay. And then we look at E of n, and this is kind of similar to what Samson had in his talk. This is the set of commutative phenomenon sub-algebras of n, and these are very often called contexts. And the idea, of course, is that within every abelian subalgebra you have a compatible set of physical quantities that can all be measured simultaneously, can all have value at the same time. So you cut up your big, difficult non-commutative algebra into these pieces, and then you construct the topos over this concept. And the first thing to think about for quantum states is what would be the analog of such a probability measure. And that's not totally obvious because you have to find some space and some collection of measurable subsets or sub-objects that we describe. So for this you can use the result 2008 is states on n, and these are all quantum states you can think of, pure, mixed, everything you can think of. They correspond objectively to probability measures. These are somewhat generalized probability measures on an object which is called the spectral free sheaf. Just have time not to find this. The point is that the spectral free sheaf takes the role of this x, so this is where our measures are defined, and the measurable subsets actually are so-called floating sub-objects. So it's a bit like here, M, I'd say it's not every subset is a measurable subset, so it's a family. What I'm saying here is states, well, that's called state rho, and the probability measure is called mu rho, and so mu rho will map from, let me keep this in the middle, and I'll just write cosine diagram over here.
So your x now isn't a set anymore, it's a accretion.
Sorry, say again?
Your x now isn't a set anymore, it's accretion.
Yes, this is not a set anymore, this now is an object in this free sheaf topos over this base category.
Yeah.
So basically what we knew before this paper was this result, that you can think about quantum states in the following way. You take sub CO sigma, this is sigma takes the role of x, sub CO takes the role of immeasurable subsets, and you go via mu rho to, well, not quite just the unit interval, you go actually to global sections of certain free sheaf, and think of these guys here as order reversing functions. It's called A from B n to 0, 1. This just means to every context you assign some probability or some measure, and they fit together to form a global section. And I don't want to go into this too much. If you want a name for this, think of this as a contextualized probability, because every context now has a probability assigned to it, and it's done in a certain way that fits together nicely. Okay, so the question becomes what to put here, and the idea is actually quite simple. This stuff lives in the topos set V, N of. These are three sheaves over this category. This is what you find in our papers a lot. As well known, this is actually sheaf topos if you look at V N of the lower horizontal topology. And this is also why I have this question definitely using. And now I have to introduce this other layer of probability into it. So instead of looking at sheaves over this partial ordered set, this is what we did so far, we go to a bigger topos. We look at sheaves over V and A times is the same topological space we had before, and that comes down to taking a product from every topo actually. And then how do we get this map? It should be quite easy. It is quite easy. There's projection E1 from V and A times, so it should be like 0, 1, L just to V and A. The obvious thing, take a pair here, what's a basic open? It's a downset of V times 0. R is downside V. This map between the base, okay, that's this is the base entry of this new topos. This here is the base entry of this topos we were using so far. Once you have such a map, you can pull back sheaves that live here to become sheaves living here. And that's exactly what we do. Well, we should only do this with those sheaves where you don't expect them to depend on R. But for the sigma, which states that you don't expect this to depend on R, so we form nothing but pull back by P1, and you get sub CL. Let me just write this doubly underlined. That's the pullback of sigma with this thing. And it's the same idea as before. Instead of having a single sigma, you get one copy of sigma for every number between 0 and 1. It's very much like this map over here. And similarly, you will now want truth values in this topos, so you want global sections of the subobject classifier of sheaves over V and A times L. And the interesting thing is how to find this L. I'll tell you how to define this L. And we saw here that, let's write out, this was actually just saying you take some subobject here and you send it to this semantic bracket as is in TU. This was how this L is defined. So what you're using here is interpretation of a certain set theoretic expression in the topos. And we want to do the same thing again. What we need, like here we have something which is, well, this type, the subobject of X, and we had this was type PX, so there's a collection of subobjects, so things have to fit together in types. Now we have a subobject of sigma probably underlined, so we need again something like this T. I should also say where this T comes from. Originally this was called the truth object. Now we should probably call it a probability object. But this encodes the whole probability situation in a logical way. So let me define this T for our situation and then we're done. Except that obviously where this is the boundary. Okay. We define our T, our doubly underlined, dependent on state rho S for all T over R. By this I mean a basic open set in this topological space. The basic open set is exactly this form. So this guy here is V comma R. Just don't want to write this time. For all V comma R, we have that T rho at stage V comma R is defined as, well, you take all those open subobjects of sigma restricted to downset V such that for all V prime contained in V rho of, okay, we are using something which I will explain. S is a global subobject, which means for every component I can get a corresponding projection, and then I can evaluate my quantum state on it. So this is something which will give me a number between 0 and 1, because quantum states assign numbers between 0 and 1 to projections. So again, this is actually where something interesting happens. This object obviously has to be dependent on R. And again, you do just what you'd expected. This stage R, you collect all those sub-objects that are of measure R or greater as an additional index V coming from contextuality, which already was in the original topics. That's the only extra complication in this. And once you've done that, you can just again define psi, let's call it psi rho, which goes from sub CL doubly underlined, so from this corner of the diagram into the other corner, which is the truth values in our topos in A terms. So and you do the same thing, you take S doubly underlined and send it to S in T rho. There's a little bit to show that this actually gives a Newton diagram, what it does. And I forgot to say this, it's easy to characterize those probability measures classically, which are sigma additive, which you normally would have. This comes down to certain joint preservation this way. Just the same over here, normal states, joint preservation in a particular way. And I claim that this diagram is a logical reinterpretation of the Born rule, because the Born rule is exactly telling you how you assign probabilities to certain propositions. So I haven't said that you can take some proposition about the quantum system and you assign a certain sub-object here. And this paper from 08 already showed how to get the expectation value as the usual number. And now you can reinterpret the expectation value as the truth value in a certain extended topos. So you can completely internalize probabilities if you want to do that. And this seems to be a good thing if you want to think about objective probabilities or propensities, but it applies very generally. And the whole idea is exactly what Steve said. You take a product with this sheaf topos over 0, 1. Okay. Thanks for listening.
Thank you. Any questions or comments? Thank you.
Well, I think one question would be, I mean, how can you do this internally?
Well, the first task would be to internalize these things. So this here actually you can see as internal because we actually interpret such expressions internally. So the task would be to internalize these probability measures, which should be possible. They should map from from, well, let's let's look at finite dimensional situation first, and maybe a bit more difficult to characterize what are the, well actually we can do this, we can characterize, I can give you a free sheet with global sections of exactly what these total sub-objects are. We have done a little bit of internalization in the paper, that's not,
I mean, to put the things like, I mean, one of the ideas I understand it was that one would do things in a uniform way, so that depending on which topos one was in,
yeah.
you know, you might get classical physics coming out of it, you might get quantitative. It seems to me there's a lot of rather carefully handcrafted definitions here, so, I mean, but maybe I'm wrong. So would it come out that you would get classical probability?
No, the difference between the classical and quantum situation still entirely is in the fact that classically you start within the topos set and describe structures in this topos, and for the quantum situation you start in this topos of species over VFM. Okay, another aspect is that of course we describe many of these things which should live internally from an external perspective.
Right.
But still, for adding this layer of probability to it, we do exactly the same on the classical and quantum side, so that's not artificial.
No, well, I mean, just, you know.
Yeah.
Can I just say that I have problems with all the interpretations of probability theory.
Yes.
To put them in a nutshell, the problem with the frequentist interpretation is that in the long run we're all dead, as James said. The problem with the propensity interpretation is that nobody's ever seen the tail of a propensity. And the problem with the Bayesian interpretation is that I don't believe that physics is about what's in our heads. So
I tend to agree with all of that.
so none of the above is right.
But what else?
Well, the wonderful thing is they all give you the same formalism.
That's true. I have my doubts whether we should have objective probabilities, but on the other hand, when we see probabilities of quality arising from pure states, it's hard to argue that it's just one lack of knowledge. So there seems to be an irreducible element of probability.
Okay.
So in a sense, there's two levels of internalization going on. You go from
Yes.
sets to 0-1 value sets, and you go from sets to contextual sets, right?
Yes.
Is the order in which you do that have any influence? Okay.
I don't think that there is not actually an order. It is rather that you start from the axiomatic level, say I have a physical system, I have certain quantities, and describe this in terms of the formal language, and I look for representations. Then you would represent it in sets to get a classical description, you would represent it in the pre-sheet topos or VFM to get a quantum description. And if then additionally you want to internalize probabilities, you do this as a second step. But I don't think you can internalize probabilities and then find the representation of the formal language. At least I wouldn't know how to do it. But, well, yeah, maybe it's interesting thinking of this.
Okay, thanks again. We'll meet again at 2:30. On other days, the lunch truck should show up around this time. Today being Sunday, we don't have that, so we have to somehow find food in Old Town.